there we are. So explain how coal, oil, and gas is used to produce electricity, and nuclear as well. Nuclear is going to be a little bit different there. So I haven't gone into nuclear. I am going to change this question slightly. But as you can see by my writing as well, I've rushed this out just to try and get it. So there's three main steps. You're going to burn the fuel, whether it's coal, oil, or gas. We're going to ignore nuclear because that's totally different. That's fission. So the fuel is burnt to boil the water. So that's pretty much it. We're going to heat water. That water then is going to turn into steam. The steam is kinetic energy, and it's going to turn a turbine. And then the spinning turbine turns a generator, which produces electricity. It's pretty much the same for everything. You're always going to have a turbine, and you're always going to try to move that turbine because it's connected to a dynamo or generator. And it just, that's the way that we make electricity, because essentially it's at its basic form, you're putting in a magnet through a coil of wire, and you're just moving that magnet to generate the current. And that is pretty much it on a large scale. I'm going to go now to what is the national grid then. So the national grid is a network of high voltage power lines between major power stations. Yeah, I couldn't fit it all in. I am going to have to change this up. So it's just when you see those huge pylons with power lines, that is the national grid. And there's advantages of this national grid, which we'll come to talk about now. Explain why the voltages in the national grid system are very high. Well, if you increase the voltage, you're going to decrease the current. So there's less frictional forces as heat. So if you send a lot of current through a wire, you're going to get a lot of friction. Therefore, you're going to get a lot of heat loss. So if we were to just send high current, low voltage electricity through power lines, you're going to lose a lot of heat. Now, I know when we do electrical circuits, as we increase the current, we increase the voltage. But that is a different formula. That is V equals IR. Now we're dealing with power. So power equals current times voltage. And as you increase one, the other has to decrease. And I won't have time to prove it in this video, but there will be videos where I prove that. So you're just going to take my word. When it comes to the national grid, as we increase voltage, the current will decrease. How do we do that? We use these things called step-up and step-down transformers. So a step-up transformer increases the voltage, therefore brings that current down. And then step-down transformer, then they decrease the voltage, which brings the current back up. How these change in the national grid system. So typically, power station produce 25,000 volts. They increase that then with that step-up transformer to 400,000 volts, or 400 kilovolts. And then when we need to use it, then they'll have these step-down transformers, which bring it back right down to 230 volts, which is what we use in the UK main supply for household use. There are others they use for factories, three-phase electricity, but we don't really need to know about that. So describe how the demand in electricity changes throughout the day. So it's not always the same demand. So for example, between 12 o'clock midnight and 6 o'clock, demand is very low because everyone is sleeping. You know, I know you get people working late night shifts and through the night, but generally that's when the majority of people sleep, and therefore you don't need electricity apart from your alarm clock. Then between 6 and 9, you get a spike. And this is probably one of the biggest spikes in the day if we looked at a graph, which I haven't got here, but you will see these. You get a spike in a graph around about 6 to 9. That's when everyone's having breakfast, they're having showers, they're doing getting ready for their day, and generally using most electricity around this time. Then from 9 till 6 o'clock in the evening, it's constantly high. It varies, it fluctuates. I mean, it'll be lower in the summer, higher in the winter because we have shorter days and with daylight. But pretty much it remains constant here and there until around 6 o'clock in the evening, and then it gradually dips then as people start, just knocking off. The demand for electricity kind of goes down then until everyone's back asleep. How can the energy demand in the UK be met with different energy sources? Again, this is a box that I'd like to make bigger, because when the demand is greater than the base load, we call it the base load. That's pretty much the amount of electricity a power station can use. Can produce. So that's it's maxing out. So when that power station is maxed out, the national grid reacts by providing additional energy, and that's why it's really advantageous to have all these power stations linked up. That's why we see these big, huge power lines, because what happens is when you get a spike, so say there's a royal wedding or some sort of, when there's the Olympics and we need massive energy in one area, they will borrow off other power stations. Nuclear and coal power stations usually provide the majority of this base load, and what will happen is hydroelectric and some renewable energies, which got very short startup times. If you think about it, I'm just literally opening a tap on hydroelectric, letting the water run through to turn my turbine. That's going to provide additional energy then at peak times or at peak events, shall we say. And then we've talked about that. It says, what is a carbon footprint? The carbon footprint is the amount of carbon dioxide released into the atmosphere as a result of burning fuel, or as a result of anything really, but in this case we're going to link it to the fuel. So there's your carbon footprint. There was one about carbon neutral somewhere. There we are. What does the term carbon neutral mean? Well, plants will release the same amount of CO2 as they pull from the atmosphere. So when a tree grows, it's going to use carbon dioxide and water, and it's going to turn that into glucose and oxygen. That's your photosynthesis equation. So it's pulling carbon dioxide in from the atmosphere, but when it's burned, it releases the same amount of carbon dioxide. So it's carbon neutral. It doesn't really have an impact on, it doesn't contribute towards global warming in that sense. Which is the source that links with this term? That should be term there. And this is biomass. And then the last one, a little bit on energy transfers. Again, there's Sankey diagrams. I know it's not very clear, but each square is worth 10 joules. And that's 10 squares, I promise you, because I've said it there. This is 5 squares. This is 4 squares. This is 1 square. Your useful energy comes across to the right, and your wasted energy goes down. And this is always your input energy. So input 10 times 10 there, which is 10 squares, 100 joules. Your thermal is wasted energy, 5 times 10 squares, 50 joules. The same there for sound, 4 times 10, 40 joules. And then we've only got 1 square, which is 10 joules of kinetic energy. Now we calculate that efficiency. You'll find this formula in the front of your books. Efficiency equals the wasted energy over the total energy times 100. So because it's a percentage, you're always going to put the small one on top of the big one to get a decimal. And then you're going to times it by 100. And in this case, it's a really easy calculation. It's 10% efficient. And I think that is the paper. Yes, it is.